Okay, so we kind of ended the last video talking about phosphate and its structure. And in between, getting the last one sorted out and starting this one, I went ahead and I wrote out all 4 resonance structures for phosphate, just so you wouldn't have to watch me do that. So the difference, right, we were at a point back here where this structure here with the 1 positive and the 4 negative formal charges, we needed to make 1 double bond, but only 1. So we had to pick between the 4 oxygens. And that really means we want to draw a structure where we choose each of the oxygens for that task. So we move the double bond around. So here we have in the first structure, double bond at the top, second structure at the right, third at the bottom, fourth at the left, right? And then we have to account for the fact that we moved electrons to make that double bond. So the oxygen that's part of the double bond would only have 4 non-bonding electrons, right? 2 pairs down here and then over here on the left. The other 3 oxygens that were unchanged in each particular structure still have 6 non-bonding electrons and only a single bond to the phosphorus. That's where we would find the negative charges. So they're in different places in the different structures, right? But that represents the reality of the structure of the phosphate ion. Every bond, so looking at the phosphorus oxygen bond that is pointed upward, double bond in one structure, single bond in the other 3, that would be 5 bonds spread over 4 structures for an average of 1 1/4 bond in each structure. So the real phosphate, there's 1 1/4 of a bond between the phosphorus and the oxygen. A 1 1/4 bond, that would be a little stronger and a little longer than a regular phosphorus oxygen bond. You can actually make these observations using something like X-ray diffraction, where you can actually measure the distance of bonds. A phosphate ion, little bit shorter bonds than you would see in a structure where those are true phosphorus oxygen single bonds. Similar with the charge. Again, let's look at the oxygen at the top. Neutral in one structure, negative in the other 3. That's 3 negatives spread over 4 structures for an average of -3/4 of a charge. So these electrons that represent these negative charges are smeared over the oxygens in the atom, which is something that you can do with waves again. So the real structure, there isn't a total negative charge on one oxygen, there's a partial negative charge on each of the oxygens. Okay, definitely something we want to watch out for. On an exam, I want to see all the structures. If there are resonance structures, you need to draw them all. You will not get full points for that particular problem. So if there's resonance, draw them all. Okay, a couple more structures here. Let's see what we can get and see if we need, if we can finish off with this video, if we need another. So NO3 minus, that's nitrate. Let me go ahead and count 5 from nitrogen. 18 would come from 3 oxygens. Add another for the charge. That's 24 electrons. That sounds a lot like carbonate up here. 4 atoms, 24 electrons. If I draw out this structure, nitrogen's less electronegative, so it goes in the middle. I can just surround the nitrogen with the oxygens. That used up 6 electrons, 18 left. That's enough to put 3 on each oxygen. Right? And hopefully you're seeing we keep hitting patterns here of things we've kind of already seen before. Enough electrons left to complete the octets around the outside of the molecule. That is going to happen in a lot of cases. Now here, we really do have a similarity to carbonate because we have satisfied the octet around the outside of the molecule, but not on the nitrogen. We need 1 more bond to get the nitrogen up to having 8 electrons. It's only got 6. If we make a bond, it'll have 8. So 3 choices. We can do it from either of the 3 positions here. So we're going to want all of those to be drawn. So let's draw those 3 possibilities. Right, and at first I'm just drawing where I put the double bond. We do want to make sure that we draw in all of the electrons as well. But those 3 possibilities. Now the oxygen where the double bond is used 2 of its electrons to make that double bond. So that oxygen will have 4 non-bonding electrons. Right, the other oxygens and all the other structures, we haven't changed the fact that those had 6 non-bonding electrons. So I can add 6 to each of those. to make sure I have all the electrons in all of the structures as well. Now, as far as formal charges go, right, hopefully by now we're starting to get the hang of it. Oxygens with 2 bonds, 2 sets of lone pairs, or 4 non-bonding electrons, that's 0. So the oxygen where we made the double bond is 0, but the other 2 with 1 bond and 6 non-bonding electrons, those are negative. Now it turns out the nitrogen here is a positive, because 4 bonds to a nitrogen is 5 minus 4 minus 0 is a plus 1. So we do have 2 negatives and a positive in here. Now that means the net is minus 1, which matches the charge on the ion. And the nitrogen in the center is positive in all the structures, but the negative charges again here are smeared around the oxygens in nitrate. So there's a partial negative charge on each oxygen, and the nitrogen-oxygen bonds are intermediate between a single bond and a double bond. And we also want those arrows. So that 2-headed arrow, the resonance arrow, should be in there as well with all 3 structures. Okay, nitrite NO2. 5 electrons from nitrogen. This would be 12 from the oxygens, 1 more for the charge. We have 18 electrons here. So nitrogen should go in the middle. It's less electronegative. Let's attach the oxygens. We used 4 electrons already. Subtract that from 18, we have 14 left. 12 can go on the oxygens, right? 6 each, 12. That leaves 2, right? 2 left, they've got to go on the central nitrogen. We can't put them on the oxygen once we get to 8, but we can put them on the nitrogen. Once we run out of electrons to use, now we have to think about the octet rule. We're missing 2 electrons from the central nitrogen, so we need to make a bond, right? And this could come from either side. So those would be our 2 options, is making the double bond from the opposite sides of the molecule we're trying to draw. There'd still be a lone pair on the nitrogen. We did not move that. The oxygen where we made the double bond would have 4 non-bonding electrons left on it. And the other oxygen, we didn't change anything, would have 6 non-bonding electrons. I didn't leave a lot of space for my little arrow, but we want that resonance arrow. Now in this case, there's only 1 formal charge, 0 here, 0 here, negative there on that oxygen, and then in the other resonance structure, it's negative on the other oxygen. So in this case, the bond would be a bond and a half between the nitrogens if we average it out, and the negative charge, half of it is resident on each of the oxygens in the nitrite ion. Okay, so not bad. Need some practice probably, but you will, if you think about it, right, if you've got an open mind to what's going on, you'll probably get the hang of it. Now, the last 2 here are just an illustration of the fact that we need to watch out for these expanded octets. Phosphorus, for example, is big enough, it can go past 8 electrons. That means it could have 5 bonds. That is what happens here in this case. We can connect all of the chlorines to the central phosphorus. Now, you could draw multiple other structures. You will not find anything that works for the rules we've talked about for PCl5. If you try to connect them all in a line, you'll end up with lots of weird charges along the way and not be able to kind of satisfy the rules we've talked about. If we start like this, though, just make 5 bonds to the phosphorus. It is big enough to do that. There are 5 valence electrons from phosphorus, 7 from each chlorine would be an additional 35. That's 40 total electrons. We used 10 because we made 5 bonds. We've got 5 chlorines who each need 6. That would account for the remaining 30. And that would complete this structure. And we would actually have 0 formal charges everywhere now. So chlorine starts with 7 valence electrons. This would be 7 minus 1 minus 6. So every chlorine is 0. And phosphorus, 5 minus 5 is 0. Okay, so I think we will do one more video after this one. Let's talk a little bit more about how expanded octets relate to formal charges. But let's finish SF6, and then we'll do one more video to kind of address a couple other issues that we should watch out for and talk a little more about formal charges. Sulfur is also big enough. It can go past 12 electrons, so it's perfectly acceptable to connect all 6 of your fluorines to the sulfur. Right, now we know a little bit about fluorine. We don't want to ever have more than one bond to our fluorine. Right, so again, if you try to draw this out in like a big long line, you're going to have fluorines connected to two things. That is not good. Sulfur has 6 valence electrons. Each fluorine has 7. So 7 times 6 is 42. That would be a total of 48. Right? We used 12 here because we already made 6 bonds. That would leave 36. Right? And there's 6 fluorines that each need 6. So we have, again, just enough to satisfy the octets on those peripheral atoms in our molecule. So if we give 6 electrons to every fluorine, we find that we have not only established the octet for every fluorine, right, and we went past the octet for sulfur, so that's fine, but we also have 0 formal charges everywhere. 7 minus 1 minus 6 for all the fluorine calculations, and the sulfur here is 6 minus 6, also 0 formal charge on a sulfur with 6 bonds. Okay, let me wrap this video up there. We will come back with one to just cover a couple more issues we should watch out for, and maybe talk a little bit more about the consequences to formal charge of these expanded octets.